Welcome to the video lectures on analog electronics. Myself, Dr. Shomik Poddar, Assistant Professor, Electronics and Communication Engineering Department, Guru Nanak Institute of Technology, Kolkata. The course code is EE303, contact 3 and credit is 3. Today, I will discuss part 3 of module 4. Before going to detailed discussion of the module 4 part 3, let us review the lesson plan of this module. The topics to be discussed are feedback amplifiers and oscillators, into which the subtopics as included are feedback concept, negative and positive feedback, voltage or current, and series or shunt feedback, Barkhausen criteria, RC oscillators, phase shift and wind bridge oscillators, LC oscillator, Colpitts, Hartley's, and crystal oscillator. The instruction hour is set to 5 and the corresponding course outcome is prescribed as CO3. That means after studying this module, the student will be able to understand the effect of different feedback mechanisms in transistor amplifier circuit. The prerequisites for this module 4 are fundamentals on Kirchhoff's voltage, current law, Thevenin's theorem, BJT fundamentals and matrix. So let us start part 3. I have included the oscillator and its various types in the part 3. In the part 1, we had discussed the basic concept of feedback and negative feedback topologies. In part 2, I had discussed the several practical examples of negative feedback circuits and a very introductory idea about the positive feedback. Now, in part 3, the different types of oscillators, their frequency of oscillation, principle of operation, as well as some practical applications of these oscillators, as well as some numericals from the oscillators will be discussed in this particular part. So let us start with RC phase shift oscillator. Basically, this RC phase shift oscillator is a sinusoidal oscillator used in audio frequency range, that is 20 Hertz to 20 kilohertz. So this particular oscillator employs a RC network which provides the feedback signal and it meets the Barkhausen criteria. So it will produce some sort a stable sinusoidal signal. So this is the general block, this is general circuit of this RC phase shift oscillator. We are seeing that this is a amplifier. It may be a BJT based circuit, it may be a field effect transistor based, or it may be a op-amp based. But we are generalized this amplifier as A, whose gain is A, and the output of the amplifier is going to combinations of C and R network, that is capacitor and the resistor network. Now here I have mentioned the 3 CR network, and after that the feedback signal is going to the input of the main amplifier. So thus it will meet the Barkhausen criteria and produce a sustained oscillation of sine and producing the sine wave with a stability. Now Barkhausen criteria states that A beta, that is the amplifier gain, and the feedback factor must be equals to 1, but for practical purpose it should be set at greater than 1, and the phase shift must be 180 degree. So when the phase shift is 180 degree, keeping in mind we have designed such type of feedback network so that the total phase shift will be 180 degree, and due to the presence of three equal valued CR combinations, so therefore the individual phase shift will be 180 degree divided by 3, that is 60 degree. So therefore we can say that after each RC network there is a 60 degree phase shift, and that 60 degree phase shift will be multiplied by the 3 number of network, and it will produce the total 180 degree phase shift from the feedback from the input to the output. And this basically this amplifier will be a non-inverting based amplifier. So again there is a 180 degree phase shift from input to output. So 180 plus 180, 360 degree phase shift will occur. So therefore we will get a constant oscillation. The frequency of oscillation of this particular circuit is 1 by 2 pi RC root 6. Now the question can be arising that how this particular frequency of oscillation is coming. Basically it can be done using the Laplace transform of this circuit, but due to the complexity I am not including these tedious calculations, just mentioning the frequency of oscillation of this RC phase shift circuit, 1 by 2 pi RC root 6. Now in general, if we are introducing more than 3 RC network, then in that case what should be the expression of the frequency of oscillations? So in that case the general frequency of oscillation will be equals to 1 by 2 pi RC root over 2n, where n is the number of RC stage. In the specific example, as the number of RC stage is 3, so therefore it becomes 3 into 2, that is root 6. And to produce a sustained oscillation, the feedback factor or the feedback circuit gain should be equals to 1 by 29, and as A beta greater than 1, so A must be greater than 29. So this is a specific criteria for designing this RC phase shift network, RC phase shift oscillator. In general, the individual phase shift of the RC stage equals to phi 180 degree divided by n, where n is the number of stages. In this case, as n equals to 3, so the individual phase shift will be 180 degree divided by 3. Now we are introducing the RC phase shift oscillator using BJT. So if you are looking into the circuit, the amplifier is nothing but a voltage divider biased common emitter amplifier, where there is no external input. The output signal from the collector is coupled through this first capacitor, then the first resistor. So this is one particular feedback voltage generated due to this CR network. So the particular voltage has the phase shift of 60 degree. Again, this voltage will be divided by this CR network, and again it will produce 180 degree phase shift, 120 degree phase shift, means again 60 degree. Then after this C, it will again produce some more again 60 degree. So total phase shift will be 180 degree. So this, as we know, it is a common emitter amplifier, the output will always be 180 degree phase shift. So as the input signal, so this signal has a 180 degree and this signal is 180 degree of this. So therefore the two signals will be of the equal phase. Now its frequency of oscillation is somehow different from our previous discussion, it is equals to 1 by 2 pi RC root over 6 plus 4 RC by R. This expression is coming due to the this hybrid parameter model of this entire network, and here the HFE, that is the transistor amplifier gain, HFE must be greater than 23 plus 29 R by RC plus 4 RC by R. So this relation is quite complicated compared to the previous discussion. These parameters are evaluated using the hybrid parameter model, but due to simplicity, I have not discussed those tedious calculations. And when RC is equals to R, then automatically the frequency of oscillation will be 1 by 2 pi RC root over 10. Now this is the most easiest and most portable circuit. The students are encouraged to design this type of circuit and see the phase shift at after each RC stages. It is an op-amp based circuit. Now we are seeing that the op-amp inverting terminal is grounded and the feedback signal is connected to the negative terminal. That means it will behave as a it will behave as a inverting amplifier. So the output will be 180 degree phase shifted of the input. Now what will happen? Suppose the circuit will produce some type of output due to the fictitious signal or some noise voltage. This output will first pass through this CR network and it will produce some sort of voltage divided output which phase shift 60 degree. After that, again it will pass through the second RC network and with total phase shift will be 60 plus 60, that is 120 degree. And after that third network, it will produce 120 plus 60, that is 118. So that means this potential, this voltage which is going to the input of the op-amp is 180 degree phase shifted of the output. That means our Barkhausen criteria is satisfied. And the input, that is the 180 degree phase shifted input, is going to the negative terminal. So again another 180 will be produced. So total phase shift will be 360 degree. How fantastic one is that? And the op-amp gain is R minus RF by R1, taking the modulus value of the gain, it is RF by R1. As we know, for this RC phase shift network, A beta must be kept at greater than 1. So the RF minus RF by R1 must be greater than 29 in order to get a sustained oscillation. The frequency of oscillation is equal to 1 by 2 pi RC root 6 due to the 3 stages RC network, and the individual phase shift will be 60 degree because 180 divided by n equals to 3 here. So if in any case we are introducing the 4 RC stages, then the phase shift of individual network will be 180 degree divided by 4, that is 45 degree, and in that case the frequency of oscillation will be 1 by 2 pi RC root over 2 into 4, that is root 8. So it is very easier to design. The advantage of this RC phase shift oscillator is very stable frequency, easier to design, and it is less costly because not such heavier or costlier element is needed. this op-amp, the 741 IC is sufficient to drive this sustained oscillation. Next, we are going to the wind bridge oscillator. The wind bridge oscillator is also an audio frequency oscillator. It is also producing some type of stable, much more stable output, but the circuit design is quite complicated. It needs tedious calculations to design the accurate circuit. So first we are looking into the wind bridge oscillator, the feedback circuit. The feedback circuit from output to input is processed through a bridge type network. So this bridge is known as the wind bridge. So due to this, the presence of this type of bridge type network, this oscillator is called wind bridge oscillator. Here we are seeing that this feedback signal is passed through this R3 to the base, to the input of the op-amp, where the other input is connected to the ground via R4 resistance. So this R3 is the feedback resistor, R4 is the input resistor. This R3 and R4 basically generate the op-amp closed loop gain. Closed loop gain, it is also in the closed loop gain R3 by R4, and here we are seeing that the output is going through a capacitor and resistor series combination, and after that there is a parallel combination, and finally it will going to the plus terminal. It's a non-inverting terminal. So therefore in the wind bridge oscillator, the net phase shift will from the input to the feedback in output to the input is the 0 degree. Because first of all we know that when the op-amp is active operating at the non-inverting mode, the phase shift between the input and the output will be the 0 degree or 360 degree. Okay, so the signal is going to the RC network and series network. After that it will again going through the parallel type of network. So the net phase shift, so the net phase shift at this point will be the 0, because this will produce the 90 degree phase, minus 90 degree, this will produce a plus 90 degree, so they will cancel out. So the total phase shift will be 0 degree. So when it is 0 degree, again due to this non-inverting mode, it will produce the 0 degree phase shifted signal. The amplifier gain is set as R3 by R4 equals to 2, and the frequency of oscillation, the frequency of oscillation equals to 1 by 2 pi root over R1, R2, C1, C2. So now for simplicity, basically for simplicity, this R1 is equals to R2. For simplicity, R1 equals to R2R and C1 equals to C2 equals to C. So therefore the frequency of oscillation is equals to 1 by 2 pi RC. 1 by 2 pi RC, and the condition for sustained oscillation is equals to R3 by R4 is equals to R1 by R2 plus C2 by C1. Here this A is not the total amplifier gain. It is A means the ratio of the R3 by R4 equals to 2. The actual gain will be 1 plus R3 by R4. So 1 plus 2 equals to 3. So the gain of the amplifier must be equals to 3, so that the ratio of this R3 and R4 should be equals to 2 here. Now we are going to LC oscillator. LC oscillators actually it will handle this inductor and the capacitive network. This type of oscillator produces the sine wave at much higher frequency than the previous two oscillators. They are called, these LC oscillators are called high frequency oscillator. They are generally producing the megahertz signals. The frequency range is an order of the megahertz. Why? Due to the presence of LC network or the tank circuit. It is the generalized block diagram of the LC oscillator. It is the main amplifier. The amplifier output is going to one frequency dependent element X2, and X1 and X2 is the tapping to the amplifier. The X1 output will go to the amplifier, and X1 X2 will be parallel with this X3 element. So X1 X2 X3 all are the frequency dependent element. Now in case of Colpitts oscillator, we are seeing that this X1 should be a capacitor C1, X2 will be a capacitor C2, and X3 will be a inductor. So that means when we are designing a Colpitts oscillator, whatever may be the amplifier, first we have to design the feedback circuit. So we are keeping two capacitor in series. The middle point will be the tap to the ground, and their series connection will be parallel with an inductor. So the feedback voltage will then go to the main amplifier. So first we are seeing the Colpitts oscillator, which uses the BJT. Suppose you are seeing that within the BJT, the R1, R2 basically provides the voltage divider DC bias. This RE and CE produces the CE is called the bypass capacitor, which reduces the effect of negative feedback, and this RE basically stabilizes the Q point, and instead of the RC resistance, here we are using the RFC. RFC stands for radio frequency coil. RFC stands for radio frequency coil. Now what is the necessity of using this type of component? Because as it is of high frequency, means high frequency operation, and at the same time we have to stabilize the Q point for sustained operation. So in case of power line, if any AC from this capacitor tank circuit, if any AC of the tank circuit will try to admit with the VCC, the RFC will provides the high impedance. So there is no mixing of the AC to the DC. But if we are using a simple resistor, then there should drop will occur. So therefore, in order to reduce some drop will occur, and it will affect also the DC signal. So therefore, in order to isolate the DC with the AC, the RFC coil must be used for high frequency generation. And if we are seeing carefully the feedback signal, this is the output of the transistor, means the collector point. Now from output, from output we are connecting a capacitor C2, that is X2, with which there is an inductor terminal L. Next, the capacitor C2 is in series with the capacitor C1, whose other terminal is going to the input of the transistor, and their series connection is in parallel with the other input of the inductor. So the C1, C2 and L basically generate a tank circuit which produce the sufficient energy for sustained sine wave oscillation. the signal, the feedback signal is fed to the base of the transistor via this coupling capacitor CC. And here, as the C1, C2 are in series, so therefore we know the equivalent capacitance will be C1, C2 by C1 plus C2. That means 1 by C1 plus 1 by C2. 1 by 1 by C1 plus 1 by C2. And the frequency of oscillation of any tank circuit, we know 1 by 2 pi root over LC. So it will be 1 by root over LC equivalent. As the CLC network is in parallel connection, so it is a parallel resonance circuit. And we know that at the frequency of oscillation, this parallel resonance circuit provides maximum impedance. So maximum impedance means if we think this equivalent impedance will be maximum, then the output voltage will be maximum at the frequency of oscillation, because frequency of oscillation is nothing but the resonant frequency. At the resonance, the tank circuit will produce the maximum impedance. So maximum impedance means maximum output voltage. So at the frequency of oscillation, the maximum output voltage will feed back to the base of the transistor. So therefore, the amplitude of the frequency of oscillation will also be high. Next, we are going to the op-amp based Colpite oscillator. Just we are changing this op-amp BJT by the op-amp. The feedback signal will go to the same circuit, but in the inverting terminal of op-amp, because the total phase shift must be the 360 degree. And the gain of the circuit will be minus RF by R1, and the frequency of oscillation will be 1 by 2 pi LC equivalent, and C equivalent will be the C1, C2 by C1 plus C2. This circuit is much more stable because there are some type of non-linearity in the BJT, and op-amp can overcome this type of non-linearities also. Next, we are going to the Hartley oscillator. The Hartley oscillator basically just reverse of this Colpite oscillator in the feedback network. In the feedback network, this X1 must be a inductor L1. This X2 will be another inductor L2, whereas the X3 will be a capacitor. That means if the same circuit of the BJT will be, but the feedback network will be L1 is in series with L2, which is parallel with the capacitor also. The feedback signal will be coupled to the CC, and this RFC provides the isolation between the DC and AC. As this is the parallel resonance circuit, so at the resonant frequency, this LC network provides a maximum impedance, and it will produce the maximum output voltage, which is fed back to the base of the transistor. Now, depending on the mutual inductance, the value of the equivalent inductance will vary. Means the tapping point where we are series. So if the winding will be in the same direction, then the L equivalent will be L1 plus L2 plus 2M. M is the mutual inductance, and if the winding of L1 and L2 will be just in the opposite direction, then automatically the L equivalent will be less. That was L1 plus L2 minus twice M. So the designer should be careful during the design of this tank circuit. Always the winding of L1 and L2 should be in the same direction. So first we are coiling the, we are just generating the coil of the L1. Then when it is in, then again we have started the coiling this L2. So thus the L equivalent will be the maximum value. Now finally we are going to discuss the crystal oscillator. Although we are using the Colpite Hartley oscillator, but the design of this high frequency oscillator is quite troublesome, and the frequency stability will not suffer, it not so much good, and the quality factor of this oscillation is, of the tank circuit will not be satisfactory. So in order to remove this type of discrepancy, we are introducing a special type of oscillator at the high frequency zone, which is known as the crystal oscillator. The crystal used in this oscillation is nothing but a piezoelectric crystal. Especially, we are using the quartz crystal. What is piezoelectric material? Piezoelectric material means, or piezoelectric, whatever the pronunciation may be. Piezoelectric means, piezo means pressure, electric means electricity. So this type of material is basically has a dipole moment. It is a polar material, but dipole moment. What happens in the piezoelectric material? If we apply the pressure, then automatically it will develop some sort of potential, not difference. It will develop some type of potential. If the pressure intensity will vary, that means suppose at time instant t1 I have pressurized the material, at time instant t2 I have released the pressure. That means when I am pressurized, the material will be compressed. When I am releasing the pressure, the material will expand. So due to this compression and expansion, the mechanical behavior of this material will be changed, and this mechanical energy is converted to the electric energy. So when it is compressed, that means the pressure will be high, so high voltage will generate. When the material will expand, the pressure will be low, so at that time the voltage will be minimum. So thus, due to the continuous compression and expansion, due to the continuous expansion and compression, the piezoelectric material will generate a sustained AC signal. So thus, this concept make and is very much helpful to design a crystal oscillator. Now the quartz material can be represented by using a equivalent electrical circuit. See the left hand side, it is a quartz crystal, and which is represented by the equivalent circuit, that this is the RLC. This RLC network is in series, whereas there is another type of capacitor CM parallel with this series connection. This CM is developed due to the hanging condition. Means when I am hanging this quartz crystal into a circuit, some types of capacitor will be developed. So this is the mounting capacitor, and the series resonance series RLC network is developed due to this piezoelectric behavior. Now, as RLC in series, but the CM is in parallel, so the quartz crystal has two types of resonance mode. One is series resonance, another is parallel resonance, or it is also called anti-resonance. The series resonance occurs when this RLC will be activated. Then it will generate the maximum current or the minimum impedance. You will see that the minimum impedance occur at a frequency F1, which is series resonance frequency. So how this, now the question arises, how this series resonance frequency will develop? Because already there is a parallel capacitor is involved. That depends on the mounting. If we are connecting the quartz crystal in the series position, then there is no development of this capacitor. These three series elements will produce a resonance frequency. But if we are mounting the quartz crystal in the parallel mode, then this parallel resonance will be activated, and at that condition the impedance will be highest or the maximum. So F2 frequency will be the anti-resonance frequency. This is the crystal impedance versus frequency graph. So this is very essential to proper mounting this quartz crystal into the practical circuits. So this is the series resonance circuit, which is the BJT based. We are seeing that the BJT collector is connected with a capacitor and a crystal. So this is basically the signal, the collector signal will be coupled by the capacitor CC and with the quartz crystal. So when this signal will be produced going to the quartz crystal, it will excite the crystal in the series resonance mode, and at that condition maximum current will flow through this path. When the maximum current will flow through this path, that means when the base current will be maximum, it will produce the maximum collector current. So like that. This RFC is used to isolate the DC from the AC. And in the parallel resonance circuit, what is happening? It is actually producing the high level of current, and this parallel resonance circuit will produce a high level of voltage. As a crystal is connected parallel with the low transistor, and the feedback circuit is the C1 and C2. So what happens? The crystal will produce a maximum impedance or the maximum output. It will be fed back due to this capacitive divider circuit, and it is fed back to the emitter of the transistor, which produce the maximum feedback signal, and basically it will produce a maximum output. So now the Q factor of this quartz crystal is 20,000 or sometimes 1 million. So it's very, very high. So that means the frequency of oscillation is finely tuned. It will much more stable, and the high level of frequency can be achieved by using this quartz crystal. In microprocessor, this quartz crystal is, and the processor network, this quartz crystal is used because it will generate the megahertz, gigahertz type of signals with excellent stability. Next, we are discussing one numerical from the oscillator. Calculate the frequency of oscillation of a wind bridge oscillator having R equals to 51 kilo ohm and capacitor is 0.001 microfarad. As the oscillator is wind bridge, so automatically we have to keep in mind the frequency of oscillation will be 1 by 2 pi RC. Just putting down the value of R, 51 kilo ohm, 51 10 to the power 3, and C is 0.001 microfarad. So 0.001 into 10 to the power minus 6. So after calculation, the frequency of oscillation will be 3120.7 hertz. That means 3 kilohertz. So that's all. Thank you all for listening the lecture.